Okay, so today marks our last lecture together on this series of integral rules. Oh, this is so sad. I know everyone wanted to do integrals forever. Yeah. Okay, that's enough of that. Let's get this going so that we can really cap off all that we've learned so far on these types of functions. So we have three rules here that we're going to go over of all the inverse trigonometric functions, which will show up at times in the AP exam. So why don't we go ahead and get started with some of the methods in which we will be seeing these types of problems. So here we go. We have the integral now. Instead, we have it in the form of 1 over the square root of 1 minus u squared du. This will result in the inverse sine of u plus c. This one will show up at times because this kind of integral will never be seen before used in any of our other rules. This with being 1 over the square root of 1 minus u squared du. This will be unique to its own rule, which will be the inverse sine rule, or of course for those who are more accustomed to calling it arc sine, who might get confused with the exponent, that is the way in which we are representing that this is the inverse function of sine. Okay, not to be confused as with cosecant, the reciprocal. That it should be a very basic concept we don't really need to go over. But in any sense though, this is going to be the main thing, the main rule that we'll be dealing with. Let's go next. Into the next one, we'll have the integral of 1 over, this time, of u multiplied by the square root of u squared minus 1 du. Okay, so this one looks in a little bit different form, but still, this is going to be something that is very unique to this specific integral, which will give us the secant inverse of the absolute value of u plus c.
But what about the inverse cosine integral rule?
Well, I'm glad that you are so astute to know where the cosine went. Well, not to worry about that. The actual inverse cosine rule is going to be the same as the inverse sine rule. So let's hold off on the secant here for just a second, because I know you all are dying to know about this, is that with the inverse cosine, so let's go back here. If we had the inverse cosine of u, and we had this guy to deal with for its derivative, well, given all of our previous knowledge, if you do remember from the derivative rules, is that this ends up with the negative 1 over the square root of 1 minus u squared du. We end up with something like this, which, wait a minute, this guy is a 1-for-1 copy of that integral for the inverse sine rule, except of course for that negative coefficient. Negative coefficient? Oh dear. All we really need to do, if you can truly understand this, is that the negative coefficient can just be thrown off as coefficient rule, and it turns out, instead of calling it inverse cosine, all you really need to do is realize that this kind of integral, if we started from back here, if we were to start an integral from that result, all you need to do is call it the negative sine inverse rule. And that's all there is to it. Because that negative is the only defining factor away from the rule, we can simply kick it out with coefficient rule, and you only need to really understand one rule for those pair of functions. Isn't life so much better now? I sure hope so. In the same manner, now we have this. Let's move forward with the inverse secant. Again, it's u multiplied by the square root of u squared minus 1, all in the denominator. For these guys, these are just subjects of memory, in which once you see it, you should be able to put it together in your mind. But lastly, what I will describe as the most important rule amongst all the inverse trig functions will be this last one. It will be the inverse tangent. So let's have a look here. Our inverse tangent rule will be known as the fraction of 1 over 1 plus u squared du, and that will give us inverse tangent of u plus c. Again, for those that are accustomed with a different way of writing it, this is the same as calling it arctangent of u. Okay, so I know that this might look like not a really big deal. 1 over 1 plus u squared, like there's like two other ways to solve it, right? Isn't it just the same thing as if we used instead 1 plus u squared to the minus 1, right? And then we take that derivative? Nope. This is not the result because this results in something else entirely. We end up with negative 1 over 1 plus u squared, all raised to the negative 2 power instead, because the chain rule, first exponent rule that is, and then chain rule is going to dictate that 2u needs to come out afterwards, not matching one bit with the integral. And secondly, of course, I know some people might think, oh, then just take the natural log of 1 plus u squared, and then take the derivative. Right? This should match up exactly with that, just so we don't have to use the arctangent rule. That's not correct at all. The actual result of this is indeed we get 1 plus u squared in the denominator, but of course chain rule dictates that the derivative of the inside of the natural log will come out as a coefficient, making these two not equal to each other. So neither of these two are ever going to be used for this rule. Like I said, this is a matter of subject to memory to ensure that we are dealing with the exact same problems. So you have to commit this. Let's really clean that up there. So that is 1 plus u squared in the denominator. That instantly goes to the inverse tangent. Okay, so these rules will be coming up. Let's do one quick example problem just to show you what some other strategies will be like to solve for this, and we should be well on our way. So here we go. We have one quick example here of 1 over 9 plus z squared dz. Now, for something like this, like I've always liked to say for our students, is that we want to take a note here as to what kind of rule we're using with. So 1 over 9 plus z squared, keep in mind of course that there is nothing in the numerator, no coefficient at all for a chain rule of z squared to be taken from. That is our hint to take this note here that we will be using the inverse tangent rule. It's the 1 over 1 plus u squared du, which will give us, again, tangent inverse of u plus c. That is the rule in which we'll be putting forth here, such that we can match this with one of the derivatives from that. Okay, fairly straightforward, but of course we have a little bit of a problem now, don't we? We have 9 plus z squared. We only need a 1, and we can only use a 1 instead of any sort of other number in that denominator added to the z squared. So what can we do? Well, all we really need to do is some very simple algebra here, and we should be well on our way. We need to change that 9 to a 1. The z squared we can worry about at a different time. Right now, we really need to worry about that 9. And it turns out that what you can do is you can simply factor out a 9 from that denominator, and we can make that into a coefficient after the fact. Pretty nice. But the result of the factoring is now going to be 1 plus, and now we need to factor out a 9 from z squared, so that's going to be z squared over 9 to do some simple algebra logic right there, that if we distribute back the 9, we end up with z squared like before, so nothing has really changed. And then dz at the end of our integral. Now this is the way that we can set up to start using this rule, but not quite yet though. We need to make sure that we're all on the same page. This 1 over 9 needs to get out as a coefficient, so that's quite easy. We'll just dump out a 1 over 9, and then the integral is all the same now, 1 over 1 plus z squared over 9. Now we end up with a second issue though. We have z squared over 9, although we want just simply a u squared or one value squared. Z squared is one squared value in the numerator, 9 is its own singular number in the denominator. So what can we do here? Well, It's not that big of a problem, because if we copy down everything else up until our fraction here, is that z squared over 9, that actually is something that is able to be square rooted, or in this case factored into a square of a number. Don't believe me? Well, we can actually end up with this. It'll be z over 3, because both of them can be had their square roots taken out. So z times itself, of course, will be z, and then 3 times itself will be 9. But now, instead of calling it z squared over 9, we can take the entirety of this fraction and call it z over 3, all of that squared, dz. Now we're really cooking here, because we have z over 3, all of that squared. That does match in that sense of being one singular value. All of that squared is 1 over 1 plus all of this squared. And now we can use the inverse tangent rule. So let's get around to that. We have that 1 over 9, okay? And then we have the inverse tangent of z over 3 plus c. Okay. Now, before we all run away out the door, never to talk about integrals again, we have this issue though, is that z over 3, we did not take account for its chain rule. Remember that in our case, because the du just turns into 1 there, the generic rule seems like everything is hunky-dory and we're all good to go. But no, we have the z over 3 here, in which if we were to take the derivative on this, we'd end up with some problems. One, of course, being that everything here will then be multiplied back into what we had from the start, except for the fact that this guy will then end up with 1 over 1 plus z over 3, all that squared. So that seems fine. But again, the chain rule will next dictate that we're going to have 1 over 3 being multiplied as a coefficient. And we can't have that. The 1 over 9 is helpful to us because that is still staying from the original problem. So that 1 over 9 will stay exactly where it needs to. But of course, this unaccounted for 1 over 3 is going to be a problem. So let's go one more time and let's try to fix that. Of course, we need to slap on another 3 to cancel out with that 1/3 over 9 of the tangent inverse of z over 3 plus c. Now this is our second proposed answer. We can clean this up to a 1/3 if you'd like. So we can call that a 1/3 just as a reminder. We can throw that into our final answer here later. But if we were to take the derivative of this guy now instead, hopefully we can end up with something that we like. So for our case though, let's leave it as 3 over 9 just for the sense to make life easier for all the canceling that we're going to do. And then let's do the tangent inverse derivative, which will then turn into exactly this. So it's going to be 1 over 1 plus all of z over 3, all that squared, times a 1/3. And of course, the plus c goes to 0. Okay, very good. Remember, that's whatever's inside of the inverse tangent getting squared in that denominator part. And of course, chain rule being sent out one more time with that 1/3. So we can start canceling out the 3. And then we end up with, if we really want to make sure we have everything lined up here, we have 1 over 9 multiplied by all of 1 over 1 plus, let's do the z squared over 9. And so the 9 can now distribute into each of those guys because they're all on the denominator. That's some good old algebraic distributive property. And so we end up with 1 over 9 plus z squared. That is a 1-for-1 match through and through for what we started with from the beginning. So that's pretty good. So let's go ahead and clean this up one last bit here. Let's erase out the 3 over 9 and let's throw in the 1/3 that we want. Forget the derivative for the time being. So our ending up with our second iteration will be 1/3 of times the tangent inverse of z over 3 plus c. Now that is how you do this kind of problem. So all it really is just another type of rule with all the same kinds of checking and changing that we need to do in order to have us match exactly what's needed. So with that, we're going to have one more set of example problems tomorrow, and that will truly conclude our first segment together on basic integration. So now we're really at the end steps here to a full recovery from cannot integrate. But from there, we have a lot more subjects to discuss. And better yet, you can tune into my live stream over here with some of the times and schedules, and you can come and answer in real time all the questions that you might have. Again, the schedule will be right there, and so we'll be looking forward to you the next time we get to meet either in video or if you tune into any of the streams. Thank you very much, and we'll see you one more time tomorrow.